All right, ladies and gentlemen, so if you have not pulled your homework out, please pull your homework out, and I will very slowly glance through these answers so you can check your work. Question number 1, we factor cancel out the x minus 3 factor, substitute 3 into what's left, we get a limit equaling 1/8. Question 2, we factor, and then we were able to cancel out the factor x plus 1, substitute -1 in for x, and what's remaining, we get out -9. Number 3, we are able to factor the numerator and able to factor the denominator, which then allows us to cancel out x minus 2. Substitute in 2 for what's left, we get out -1/4. Number 4, you did have to do by factor by grouping. I know I did not do one of these in our notes. If you got this, give yourself a high five or high five. You do not have to know how to factor by grouping on the final. But in this case, I did group. You can see in my pink parentheses, I did group the first two and the last two, but because of that subtraction sign in the middle, you have to change the inside sign. And once you factor out what is consistent between each one of those, you can see my work. X plus 4 is a common factor now, so we factor out what's in common, and what's left was x squared minus 1. That x plus 4 is what gets factored once we do a GCF in that denominator, and substitute -4 in. Again, this is a factor by grouping. If you don't know how to do this right now, this is okay. I did cancel those out on your notes, and you do not need to know how to do this on your final. We canceled those. I did the conjugate of the denominator. You can see my work in the Punnett square. The factor of x plus 2, it cancels out. Once you substitute -2 in, what is left, we get a limit of 6. The next question, it ended up not working out very well. I thought maybe I could change it to an x minus 1 and we could cancel out the x's, which I can, but then you get an imaginary answer. I wasn't a big fan of it, so just go ahead and cut that one out. If you do want to practice a little bit more conjugates, those two are nicer. You can practice those, but please make sure you know how to do a conjugate problem for your final. Fast forward, looking at this first function, the top represents the left, the bottom represents the right. So at 1, we have to check both left side, right side. The y values are different, so the limit does not exist. Part B, as x goes towards 4, we just have to plug that one into the bottom equation because 4 is bigger than 1. So substitute 4 in, we get out 8. We have an absolute value function and a totally horizontal line. Y equals 2 is a horizontal line. So the top equation represents the left side of 4. The bottom equation represents the right side of 4. So at 2, we just have to plug it into the top, get out a limit of 0. Part B, at 4, your left side ends up at 2. Your bottom, there's no x to plug into because it is a horizontal line. So no matter what x value that you use, the y value will always be 2. They are the same, so the limit exists at a value of 2. And part C, as x goes towards 6, that's your bottom equation. Your y value will always be 2. Again, because it's a horizontal line. And the last two, substituting your x value in, solving for a, knowing that your left side has to equal your right side. Those are the work. In the first problem, you get an a value of 1. In the second problem, you get an a value of -1. This video will be available on Schoology. If you do need to see my work for homework a little bit closer, a little bit slower, I have posted it as an update on Schoology. Please just watch the video on your own time. But I do want to get into the notes that we need to get done for today. So turn to page 10. We started talking about discontinuity yesterday in class. And just as a reminder, when you can factor and then cancel. That is where we have a hole. Some people call it a point discontinuity. And when we see a graph, you may potentially see something and then a hole and then finish it out. That might just be an example, but there is literally one point or one x value, maybe more than one, but anytime that you can factor cancel, that will give us a hole or a point discontinuity. When you can't factor cancel and you have a rational equation where you have a denominator that has a value that could be 0, then you have an asymptote. And what you'll see on a graph is you'll have this vertical line, and potentially you might have a graph that approaches that asymptote on both the right and the left side. And then last but not least, we have a jump. This will happen in piecewise functions. I showed you guys this in class. Sometimes when we stop graphing one graph and we start graphing another, there is a disconnect in what you have to graph. So you are jumping from one to the next. Now, I do want to let you guys know that just because you stop graphing one graph and go into the other, it is very possible that you have an open circle for one, but then when the other one comes in, it fills in that gap. And when you stop graphing the parabola and you start graphing the line, they do have the same y value. That's what we were solving all that A for in that homework. So it is possible for the limit to exist in those situations, but sometimes they don't. So we've got holes, we've got asymptotes, and we've got jumps. That's the discontinuity types. So if we're looking at this graph, we are stating the x values where it is not continuous. So it is not continuous at holes, jumps, and asymptotes. So I would see a jump right there at the x value of 1. I see an asymptote right there at the x value of 2, and everything else looks pretty good to me. So we would say at x equaling 1, there is a jump, and at x equaling 2, there is an asymptote. So where is it continuous? Well, it's continuous all on this. We don't have any holes, jumps, and asymptotes up until 1. And then we start being continuous again from 1. We're looking at the x values now from 1 until 2. And then we jump over here on the other side of the asymptote, and it looks like we are continuous past 3. So I'm going to go through here, guys. This chunk of the graph we would call continuous from negative infinity up until positive 1. I would use a bracket because at 1 there is a jump. I am not continuous at 1. Just so you can follow along with me, I'm going to look at this part of the graph right here that I'm going in blue. So we would say in union with from 1 up until where that asymptote is at 2. And last part that we're continuous, where we see that there are no holes, jumps, or asymptotes, is this chunk on the far right. We say and union with, we start graphing again at 2, and we go out through positive infinity. So I want you to identify the fact that I said x equaling 1 was a discontinuous spot, and if you look at my breaking points in the continuity, we have a breaking point at 1. So we can see I stop graphing 1 and start graphing another right there. And we also identified that 2 was an asymptote, and you can see that right within my intervals. I stop graphing 1 at 2 and I start again at 2, but 2 is not included because I don't have a bracket on there. So this is a bad question. It is not continuous at, let's change that to 2. And we would say there's an asymptote there. It is not continuous at 1 because of a jump. And we kind of already explained this one, so let's cross that guy out. Holes happen when we can factor cancel. Jumps happen when we change one graph going into another. That happens typically on piecewise functions. And asymptotes happen when we have some sort of rational, which means we're dividing, because again, we cannot divide by 0. So if I look at this one, we're deciding where it is not continuous. Well, where things are not continuous, we identify situations where we've got denominators. Denominators are no good for us. The value that would make that denominator 0 is at x equals -1. We would have to not use -1. When in doubt, natural log is a function you have not seen in a very long time. So let's pull up our graphing calculator. And let's see what that natural log graph looks like. So if I go to y equals, and I click my natural log of x, and I graph this. I have to turn my plots off, I'm sorry. I'm not sure why that box plot is still showing up. I turned my plots off. Anyway, but if we take a look at this graph, your natural log graph is the one that's curved. Don't mind the box plot in there. And we can see that it does approach that asymptote at x equaling 0, and it does continue forever. So we would say it is, if we were to do a sketch, we would have an asymptote here at x equals 0. It would approach that asymptote, and it will go forever in that direction. So where are we not continuous? Well, we actually are continuous everywhere. There are no holes in the entire function. You could say that we are not continuous at x equals 0 because of that asymptote location, but the actual natural log graph is continuous. You are not going to be graphing natural logs anywhere on the final, so don't worry about that. The next one I do want to take a look at is your absolute value. So I hit my math button, I scrolled over 1 into number, and it says ABS. So let's plug in an x divided by x. I do want you to see this graph, so please pay attention to this one. And what happens with this guy is we're looking at a graph that goes here and then here. Okay, there are 2 horizontal lines going on in there. So where we have an issue is we stop graphing one and we start graphing another. We actually have 2 holes there because you can never divide by 0. So where do we have an issue? We have an issue at x equals 0. And that is a graph that you definitely should remember what it looks like. If I'm looking at this one, denominators are pretty easy. If I stick 1 into that denominator, that would make my denominator 0. Can't divide by 0. And in this case, I care about factoring that denominator. This would factor into, I would have a 9, that would be 18. That would be 16. And 3. -12 and -3. There's my factors for that bottom. So x would not be able to be 6 or +3/2, setting each of those factors equal to 0. Setting each of those factors equal to 0. That is where I'm getting 6 from. and 2x minus 3 equals 0. That's where I'm getting 3/2 from. The numerator doesn't totally matter. They're just asking me where am I going to have issues, whether they're a whole jump or asymptote. That isn't the question on this one. I'm just truly finding those excluded values. Looking at this next function, we can see that at x equaling -3, we would have an issue. If I factored out an x in that denominator, I would have x times x minus 4, which would mean the values that would give me a 0 in the denominator are 0 and 4. Now we can do this one pretty quickly. This x would cancel out that x, so we do know that that would be a whole, where that would be an asymptote because it doesn't cancel out. Piecewise functions, such as this one, are going to be where we have a jump, but in order for me to know if there's an issue, I have to check my left side. It's left because it's less than 0, and my right side, it's greater than 0. So if I stick -2 in for the left-hand side, I get out 2. That's my y value on the left. If I stick -2 in on the right-hand side, I get 4 minus 11. 4 minus 11 is -7 for my right-hand side. Because my left and my right don't match, I know that there is a jump at x equals -2. And last question, guys. I factor out an x. I have x plus 3. So therefore, I know that there's actually an asymptote because it doesn't cancel at both x equals 0 and at x equals -3. That numerator, x plus 7, does not cancel either one of those out. So looking at this homework, all you guys have to do is kind of identify whether what type of discontinuity it is. And you are looking at specific spots and telling me whether it's a whole, a jump, or an asymptote. So something like this question, I just want you to understand what we're saying is essentially I'm saying, do you have an issue at x equals -3? So if I did this question, I would have x plus 1 in my top. I would factor the denominator. The denominator does not factor. So therefore, if I decided to plug in -3, let's check that denominator. What would happen if I stuck -3 in there? I'd have -3 squared plus 2 times -3 plus 2. Remember, continuity or issues happen when I have 0 in the denominator, which is why I'm only focusing on that denominator. And you can quickly see here that I would not have 0 in the denominator. So the question says, determine if each function is continuous at the given value. And because I actually will get out an answer, I will get -2 over 5. I would say, yes, it's continuous. If I got 0 in my denominator, I would say, no, it is not continuous, or we would call it a discontinuity. And you would, if you can factor cancel, tell me it's a whole. If you can't cancel it out, tell me it would be an asymptote, or something like number 6 with a piecewise, you would have a jump if it doesn't have the same y value on the left and on the right. For this next part, you're going to tell me where there are potential asymptotes or jumps. All right, so that is your homework. I will shorten this up a little bit. I do want you to identify some issues. If there aren't any issues, then you are continuous from -infinity to +infinity. But I will cross this one out and I will cross those out. I will shorten up homework a little bit. And we'll cross 22 out. Again, if I am flicking this off too fast, please go ahead, refer to the YouTube video. Have a great weekend, everybody. Thanks for your attention.